Hello and welcome to another Year 10 Chemistry revision video here. Today we're looking at the Triple Award paper for 2017 and it's a higher tier paper. So the following diagram shows an outline of part of the periodic table and the letters shown are not the chemical symbols of the elements. Now the first thing that I would like you to do is when they've got this where they've not given you the exact symbols, you're going to use your periodic table to work them out. So A is beryllium, B is neon, C is magnesium, D is silicon, and E is sulfur. And this is going to be really handy answering these questions. So first one, the two elements in the same group. We're looking for now the two which are in, the word group means column, and A and C are in the same column. Notice how, guys, I've used A and C, and even though I've worked out what they are, I haven't put in beryllium and magnesium. I've still used A and C. The element which has 12 protons in its nucleus, if I look at the periodic table, 12 protons is magnesium, and magnesium is letter C. The element with a full outer shell of electrons, well, anything with a full outer shell will be in group 0. That gives me B, which is neon. The element in group 2, period 2, well, I've just written the group numbers along the top, and I've put the period down the right-hand side here for you. Well, I'm going to go to group 2, and I'm going to go across for period 2, which is A. Remember, periods, we don't start counting from the left, we go from the top right. And finally, the element with the electronic structure 2, 8, 4. Well, added up, that equals 14. And I can look at the periodic table. I know that 14 would be silicon, and silicon I've already worked out is D. So I'm going to put D by there. Diagrams 1 to 5 show the electronic structure of 5 elements in the periodic table. And again, guys, I'm going to work out what they are. So this here, I've got nitrogen, boron, silicon, hydrogen, and I've got neon. And I've worked that out by counting the number of crosses in total. For example, nitrogen, that one there has got 7 crosses. Give the number of the diagram which shows the electronic structure of the element which lies directly below this one in the periodic table. Well, this one has got 6 crosses, so that makes it carbon. In my periodic table, silicon is below carbon, so silicon is number 3. I could also work this out by the fact that this one is in group 4, period 2, and this one is in group 4, period 3. And then looking to the left of this diagram, which is helium. Well, to the left of helium is hydrogen, which is number 4. Nitrogen has 2 stable isotopes, nitrogen 14 and nitrogen 15. Describe how both of these isotopes are similar to one another and how they are different. Well, first thing, remember an isotope, they've got the same protons. Well, both of them have got 7 protons, because their symbols will actually look this way. So their atomic numbers will be 7. The difference, though, is nitrogen 14 will have 7 neutrons. And I've done that by doing 14 take away 7. And nitrogen 15 will have 8 neutrons because I've done 15 take away 7. A student carried out an experiment to investigate the speed of a reaction between a lump of magnesium carbonate at mass 0.32 grams and excess dilute hydrochloric acid at 20. We've then got a piece of the apparatus here, and they measured the total volume formed every 5 minutes for 40 minutes. We've then got the results for this, but we've got a missing number at 15, and they've asked us to use below to find the volume formed after 15 minutes. Well, when we measure the volume, we measure from the bottom of the meniscus. So we measure from the bottom of the curve, which means that 60, 61, 62. The tough thing we got to work out, guys, is that it's counting up in ones going down. We're then going to be needing to use this information in future pages to look at graphs. So make sure you're flicking back and forth throughout. Because on the next page, I've had to plot those values, and I've included the missing value at 62 as well. Have a look at my curve of best fit. It's lovely and smooth. Also have a look, guys, that I included my cross at 0, 0 because that was in the table. I've labelled that X as well because that's what they've asked me to do. They then asked me to sketch the graph you would expect if the experiment were repeated using 0.32 grams. Now, if you flick back, that's the exact same mass of magnesium carbonate. But this time, instead of a lump, we're going to use a powder. So this is what we need to be thinking. If I use the same mass, I'm going to make just as much gas. So that's why my finishing point is in the same place. If I use a powder instead of a lump, it's going to be faster, and a faster line is a steeper line. So look, my line here is steep, still a smooth curve that ends in exactly the same spot. State and explain the effect using particle theory, the effect of increasing the concentration of the acid. If I increase the concentration, there are more particles, 1 mark. So more collisions are likely to occur, 2 marks. This will lead to a higher rate, 3rd mark. I've stated the effect by saying it's a higher rate, and I've explained why. The student then investigated the same reaction using a different apparatus, and a lump of magnesium carbonate was added to excess dilute hydrochloric acid at 20. Now I've got the results of this. This time we've used a mass balance. So my mass at the beginning was 179.8, and my mass at the end, after 60 minutes, was 179.63. The change in mass was recorded for 60 minutes and displayed on a graph on a computer, and the reaction took 40 minutes to complete. So what I want you to know is that the reading on that was after 40 minutes, so it's been 179.63 since then. So what I did is I added some crosses to show this. My starting cross was 179.8. My finishing cross after an hour was 179.63. But I know that it's been that way since 40, so I put another cross there, and I've simply joined the dots. So we've got a literacy question here, guys. What I'll do is I'm going to go through the answers, but just a little reminder for you. Always read the questions before you read the information, so you know what you're looking for. And if you have to go back a couple of times because there's more than one question, that's absolutely fine. So tick the box next to the main reason why countries are building desalination plants is because climate change is affecting the availability of water. Tick the statement which best describes how the graphene sheets desalinate the water. We can see this from the picture on the previous page, and that's the sheet contains holes which are bigger than water, so the water fits through, but smaller than sodium and chloride. And then finally, our question here, the total volume of water on Earth is 1.4 times 10 to the 10. 97% is seawater. Most of the remaining 3% is bound up in ice, leaving 0.3% as fresh water. Calculate the volume of the Earth's available freshwater and give your answer in standard form. So I've got to find 0.3%. So I'm going to do 0.3% of 1.4 times 10 to the 9 is 0.3 divided by 100 times 1.4 times 10 to the 9. And that's going to give me an answer of 4.2 times 10 to the 6. One piece of survival equipment found on life rafts is a solar still. Solar stills are used to remove soluble salts from seawater to form drinkable water. State and explain the physical changes that occur in the formation of drinkable water from seawater, including the name given to the overall process taking place. So if we have a look at our diagram, we pour seawater into our basin. We've got this here, which signifies a gas being produced. So the water is evaporating. It hits the plastic dome, And then rather than falling back in with the seawater, it trickles down the side when it condenses on that cold plastic dome to give us drinkable water. So we're looking at here, they're asking us about how can we separate solids through evaporation. So we've got energy from the sun evaporates the water rises and condenses as it cools on the dome. This is an example of desalination. This is a triple only question for A and B, but everyone can do C. So I will talk through A and B, and if you need to fast forward, you may. Okay. I'm going to read straight to here. Many people argue against the opening of a quarry in the area, despite all the benefits of limestone quarrying. Explain 2 reasons local people might use in an attempt to stop the opening of a quarry in the area. First one, we've got heavy traffic, which will lead to levels of noise and air pollution. And 2, the formation of the quarry destroys the landscape, which is unsightly and can destroy habitats. When limestone is heated in a lime kiln, thermal decomposition takes place. Write a symbol equation for this. I go from calcium carbonate, which is limestone as a solid, to form calcium oxide, which is quicklime, plus carbon dioxide gas. Must know, guys. Okay, this is one for everybody now. Calcium silicide is a compound containing calcium and silicon only. A sample of calcium silicide was found to contain 2 grams of calcium and 2.8 grams of silicon. Calculate the simplest formula for this compound and you must show your workings. Well, we've got a simplest formula, or what it may also be known as, guys, just remember it could be called empirical formula. So I have a column for each element. I've got calcium and silicon. I place the mass of each one at the top. I divide that by the mass number on the periodic table. So 2 over 40 and 2.8 over 28. I then circle the smallest number and I divide all columns by that. That gives me an answer of 1 and 2, which gives me the simplest formula of Ca1Si2. Gwyn carried out an experiment to find the solubility of potassium nitrate at room temperature, 25. And the method he used is shown in stages 1 to 3. Now we're going to go through this method in a bit of depth. So the first thing he did, he added solid potassium nitrate to 50 centimetres cubed of water until a saturated solution was formed. So what he's done there is no more will dissolve. That's what saturated means. The maximum amount of potassium nitrate is in there. He then pipetted, he removed 25 centimetres cubed, so half of that saturated solution, into a pre-weighed evaporating basin. Now this water is very, very salty, and he put the basin and the solution into a warm oven. So he's going to heat the water. He removed the basin from the oven and allowed it to cool, and he weighed the basin and the crystals after 2 hours. His results are shown below. So the mass of the basin is 42.6. The mass of the evaporating basin and the crystals is 54.2. So what that means then is the crystals on their own are going to be 54.2 take away 42.6. And that's going to give an answer of 11.6 grams for my crystals. So first of all, state what is meant by saturated solution. So no more solid will dissolve. We've spoken about that before. Use Gwyn's results to calculate the solubility of potassium nitrate in 100 grams of water. So just remember, we used 25. So we used a quarter of that. So first thing we're going to do is that little bit of maths that we've done there. We're going to find the mass of the crystals on their own was 54.2, take away 42.6, which gives us 11.6 grams in 25. They want it in 100 centimetres or grams of water. So I'm then going to times that by 4, because 4 times as much will fit in 4 times the water to give me 46.4 grams. Gwyn's experimental value for the solubility of potassium nitrate is much bigger than expected. Suggests how Gwyn should adapt stage 3 of his method in order to get a more accurate value. So what they're saying is he's got more mass than he should think. Now I want you to think, your clothes will weigh more if you've worn them outside in the rain. So the reason why he will have a higher mass is his crystals are still wet. So, first reason, not all of the water may have been removed during the heating. So Gwyn needs to heat the basin for longer. Gwyn was asked to find out if sodium chloride is more soluble in water than potassium nitrate. State which variable Gwyn must keep the same in this experiment in order for him to compare the two. Well, we're going to have to do it at the same temperature, so we're going to keep that exactly the same. The solubility of potassium bromide at 20 degrees is 64 grams per 100 grams of water. Calculate the mass of solid that forms when a solution containing 43.9 grams of potassium bromide in 50 grams of water is cooled to 20 degrees. So first thing, if it's 64 grams per 100 grams of water, well, that means that 32 grams will fit in 50 grams of water. Half the water, half the amount. So that means then there isn't space for all of our salt because I've got more than 32. So what we're going to do, we're going to do 43.9, take away 32 to give 11.9. Calculate the number of moles of potassium bromide, KBr, in 64 grams. Give your answer to two significant figures. Well, we've got the number of moles. So you can see on the left-hand side, I've drawn the moles triangle. So I know I'm finding moles, which is N. And N equals mass divided by Mr. My mass is 64. My Mr, I've got 1 potassium plus 1 bromine. So I'm going to do 64 divided by 39 plus 80. And that's going to give me 0.54. Okay, the bar graph below shows the densities of 5 group 1 metals. Draw a straight line on the bar graph showing the general trend in the density of group 1 metals. How does your trend line suggest that potassium and not sodium is the anomalous density value? Well, I can see if I go through the top of each bar, potassium is a lot further, its tip is much further from the trend line than sodium. The flowchart below shows some reactions of group 1 metals. I've got a flowchart. State and explain one similarity and one difference you would see when lithium and potassium are both added to cold water. Well, that's this flowchart there. My similarity is they both fizz. My difference is potassium will burn with a lilac flame, but lithium will not. Write a balanced equation to show the reaction between lithium and oxygen. Well, I've got 4Li plus O2 gives me Li2O. And the way that we work this one out is I know that lithium plus oxygen will give me lithium oxide. So I'm going to go to the back of the booklet to the ions table. And I'm going to work out from top, swap and drop the formula of lithium oxide. So I know that lithium oxide is going to have to be Li2O1. Oxygen, just like the halogens, doesn't like being lonely, which means it's got to be O2. And lithium is going to be on their own. So I need to balance this up. I need to balance up the oxygens first. I need a big 2 there, which now means I've got 4 lithiums. The boxes below show some of the elements in group 1 and group 7. Explain in terms of electronic structure why potassium and chlorine would react most violently. We have got to remember that group 1 becomes more reactive as you go down, and group 7 becomes more reactive as you go up. So the two most reactive in those boxes are potassium and chlorine. So I get 1 mark for remembering that. I then say that potassium is the most reactive alkali metal because its outer shell is furthest from the nucleus, so it's easier to lose. Chlorine is the most reactive halogen because its outer shell is closest to the nucleus, so it can gain an electron more easily. The diagram shows an ion exchange column used for softening permanent hard water. They've given us some information here. They've told us that it contains sodium. Nice clue for later. Explain how the ion exchange column works. Hard water contains calcium and magnesium ions. The sodium ions on the bead swap with calcium and magnesium in the water. Explain why the ion exchange resin will stop working after continuous use, and name a solution which can be passed through the resin to regenerate it. Well, the sodium's going to run out, so all of the sodium ions have been swapped for calcium and magnesium. They can be regenerated by passing a salt solution, for example sodium chloride, through the column. Describe and explain a method to test whether a sample is soft water, temporary hard water, or permanent hard water. So, I'm going to measure 10 centimetre cubed of the water sample. I'm then going to add 1 centimetre cubed of soap to the sample and shake 10 times and keep doing this until a lather forms. And I'm going to record that volume. I'm then going to boil all the samples and repeat the process. If it's soft water, I will not require much soap at all before boiling. If it's temporary hard water, I'll need a large volume of soap before boiling, but at a low volume after boiling. And if it's permanent hard water, I'll need a large volume of soap before and after boiling. In the table below, shows the results of tests carried out on 3 white group 1 compounds, A, B and C. The flame tests were carried out on the solids and the silver nitrate tests on solutions. So, compound A had a red flame test and a white precipitate. I know it's group 1, so I don't have to worry about could it be brick red? Because brick red is calcium, which is group 2. So the other red one is lithium, and a white precipitate is chloride. I've then got a yellow flame test, which is sodium, and cream, which is bromide. And I've got a flame test of lilac, which is potassium, and a yellow precipitate, which is iodide. The symbol equation represents the reaction occurring between solutions of silver nitrate and magnesium chloride. Write the ionic reaction, include state symbols in your answer. We've seen this in a previous paper. The silver and the chlorine react to form silver chloride. So I look at the back, I see silver's Ag plus and it's a solution because I can see the AQ there. So I'm at AQ, aqueous, dissolved in water. I've got the chloride, which is Cl minus, which is AQ. And then I get silver chloride as a solid. I don't need to worry about the 2's or the little 2 after when I'm doing an ionic equation like this. W, X, Y and Z represent the halogens fluorine, chlorine, bromine and iodine, but not necessarily in that order. The diagram below shows some reactions of W and X. So, when we form W, we get a solution of W ions, which means, everybody, that W has stolen the sodium and iodine is left on their own. So I know straight away that iodine is Y, and I know that W must be more reactive. When I have W here, when it reacts with sodium bromide, I get another solution. So it's stolen the sodium, which means that X must be bromine. So I know then it could only be fluorine and chlorine left. However, there is no reaction between W and Z, which means Z must be more reactive. So W is chlorine and Z is fluorine. Iron wool burns in fluorine to give iron 3 fluoride. Write a balanced symbol equation of this reaction. I can see I've accidentally done this for chlorine there, so I just changed them. But what we need to remember, guys, okay, and I'll talk you through it. We're going to have iron plus fluorine, and it's got to be, they told me it's iron 3 fluoride. So I'm going to have fluorine is a halogen, it doesn't like being on its own, F2, and iron is Fe. And then I look then for top, swap, drop. Again, I've got to find the formula. I've got to go to the back of that book. And I find that as my final formula. And then it's a case of balancing things up. Okay. Final question on this paper then. Explain what happens at a destructive and constructive plate boundary. Diagrams may be included in your answer. So, at a destructive plate boundary, oceanic and continental plates move towards each other and collide. We could just say two plates of different density. The denser oceanic plate is forced under the continental plate. The friction causes earthquakes. Volcanoes are formed when the plate melts. Constructive plate boundary. Plates move apart from each other. Magma rises through the gap and forms new rock as it cools. We could also add on the end, and volcanoes. Well done on getting to the end of this video and completing this past paper. If you've got any questions, please come and see me or another member of the science department and we'll help answer any of your queries. Good luck with the rest of your revision.